まずはじめに、汎用基盤技術研究グループ、グループディレクター、杉山正史より、汎用基盤技術研究グループの紹介を行います。杉山グループディレクター、よろしくお願いいたします。
はい。それでは、杉山から、汎用基盤技術グループの紹介をさせていただきます。汎用グループでございますが、機械学習の理論構築、アルゴリズム開発を行っていこうということで、基礎の数理から学習理論、最適化の理論構築、さらには学習推論、探索、検定のアルゴリズム開発といったレイヤーの研究を行ってきています。そしてこれらを、実用につなげていこうというのが最終的なゴールとなります。で、現在、13チームございまして、今年度2チーム新しく新設いたしました。で、これが、高次元因果解析チームと、蓄次意思決定チームです。で、この2名の新しいチームリーダーに今日のパネルディスカッションに参加していただいてますので、彼らの研究のビジョンについて今後、この後伺っていきたいと思います。で、今日、この私のプレゼンの中では、今年度汎用グループで得られた興味深い研究成果をいくつかかいつまんでご紹介させていただきたいと思います。まず、継続学習というテーマに関しましてですが、今、機械学習のシステムをトレーニングしたときに、一回学習して終わりではなくて、それを、実世界に実際に、ディプロイして、追加的にどんどん継続的に学習させていこうという技術になります。で、これ当然ながら大規模言語モデルでも、非常に重要な技術となっています。で、これに対して AIP センターのメンバーがいろいろ研究を行っておりますが、例えば分布シフトへの対応ということで、時間とともに、データを生成する確率分布が、変わっていくことがよくありますので、それらにうまく適用できるようにしていこうという研究が行われておりまして、テクニカルには同時確率分布シフト化でどうやって分布外適用をしていくかといったトピックであったり、あるいは連続的な強変量シフトに追従していこうというオンライン学習法であったり、でこういったものが、昨年度発表されています。で、さらに、継続学習では、一般的には、限られたメモリ有限のメモリを持って、重要なデータを、保存しておいて、忘れないようにしようというような工夫がされますが、そういった問題に対して、ガウス仮定回帰において、誤差の蓄積を評価して、データバッファーを更新していくという技術を作ったり、モデルのデータに対する感度を推定する新しい方法を開発したり、さらには過去の訓練データに対する勾配を再構成することによって、学習の性能をさらに上げていこうといったこんな技術を開発しております。で、今、生成 AI が世の中を席巻しているところですが、生成モデルの、学習の最適性を理論的に調べようという研究も行っております。で、ちょうど今日、西野先生からコンピュータービジョンの話いただきましたが、画像分野でも、生成 AI の研究を非常にされておりまして、特に拡散モデル、ディフュージョンモデルと呼ばれるものが非常に、性能がいいということで注目されています。で、生成 AI ではあるんですが、ディフュージョンモデル、拡散モデルの学習の中身を、紐解いていきますと、スコア関数と呼ばれる、確率のログの微分ですね。これを学習することに数学的には対応していまして、この学習がどれぐらい精度が良いのかというのを理論的に解明いたします。で、いろいろ細かいことは、ございますが、データの実質的な次元に応じて、次元の呪いを回避できるということが理論的に明らかになりました。これによって、真の分布をある条件の下ではほぼ最適なレートで推定できるということが分かりまして、さらにスコア関数の推定は、t が0の方が、近い方が難しいということが分かりましたので、アルゴリズムをさらに改良していくには、この部分に注力するのが重要なんじゃないかということも、理論的に明らかになっています。さらには、大規模言語モデルで用いられているトランスフォーマーの、推定に関しても、ミニマックス最適性が達成できているということを、証明しています。で、さらに、平均場ランジバンド動力学という理論を作っておりますが、これは、無限幅の二層ニューラルネットワークの雑音付きの勾配学習の連続時間版を考えていることに対応します。ちょっとこれは式が書いてありますが、でこういったものに対しまして、実際のアルゴリズムでは連続時間ではなくて、離散時間で、勾配法を実行しているわけなんですが、その際の離散化の誤差を理論的に明らかにするという研究を行いました。で、いろいろ結果が得られましたが、結果的にステップ幅と粒子数と、勾配の分散というのが、和で影響するということが明らかになりましたので、これはある意味、いいニュースかもしれないですが、それぞれを独立にちゃんと改善してやれば、その分、性能が向上するということが理論的には言えるということになります。 さらに、2層のニューラルネットワークの反価誤差を理論的に解明するということをしておりまして、ちょっと細かいところはご紹介できないですが、ニューラルネットワークのサンプル複雑度がどういう構造を持っているかというのが、数学的に明らかになりました。で、K というのが、実際のデータのある意味次元に対応していて、D というのが、見かけの次元に対応するわけですが、それが分離されるというのが、非常に興味深いところで、これが、ディープラーニングを使って特徴学習をする部分の恩恵だというふうに言えるかと思います。さらに分類器の限界性能を知ろうという研究もしていまして、申し上げるまでもなく、近年の発展によって機械学習の高性能化がどんどん加速していますが、どこまでいけるのかというのをちゃんと理論的に知ることは重要だろうと、考えています。で、実際にデータから今の問題に対してどこまで限界性能いけるのかというのを推定する方法を作っています。で、この方法は、特に学習する必要はなくて、ソフトラベルだけを集めて、そこから推定するという非常に簡便な方法なんですが、ちゃんと、うまくいくことが理論的にも保証できるわけなんですが、それを使うと、例えば、iClear という国際会議は、査読の結果が、公開されているんですが、それを見て、例えば、アクセプトされた論文でも、4がアクセプトで1がリジェクトみたいな時だと、80%の、信頼度みたいなことにしておいて、推定してやると、iClear の論文歳費のベース誤差推定ができてしまうんですね。で、やってみると、最近科学史の分野、論文の数がめちゃくちゃ増えていますので、査読の質が落ちてるんじゃないかということが、誠しやかに言われているところですが、蓋を開けてみますと、こうやって推定しますと、ちょっと性能は、落ちているかもしれないんですが、思ったほど悪くないということで、それなりに、意味のある結果が得られるんじゃないかと思っています。で、これは分類器が不要でソフトラベルだけから推定できるというメリットを生かして、こういったことができるようになりました。で、さらに、正ラベルなし分類という、技術を作っていますが、で、それを音響信号の強調に応用したという研究をしています。で、通常、雑音を含んだ信号を何か、雑音除去装置を通して、綺麗な信号を取り出そうとしますと、標識学習を行うために、綺麗な信号が必要になるんですが、実際のデータで綺麗な信号を取るというのはなかなか簡単ではありませんので、一般的には人工データを使って、人工的な雑音を綺麗な信号に乗せて、ペアのデータを作って学習するということをしています。ただこれやっぱり人工的な雑音を足すことになりますので、実データに対してあまり反価しないという問題がありますが、今回の正とラベルなしデータから分類するという技術を使いますと、こういった問題を一挙に解決することができまして、雑音のある環境で集めた、雑音を含む信号と雑音だけの信号を使って、信号と雑音を分けることができるようになります。で、それによって従来法よりも非常に良い性能が得られるようになりまして、対になったデータを使った共通学習に肉薄するぐらいの性能が出せるようになるということで、これベストペーパーアワードに選ばれています。で、こういう形でいろんな成果が得られていますが、時間がありませんので、あとはこういうものがありますということで、もし興味持っていただける方がいらっしゃいましたら、ポスターが、このシンポジウムのホームページからリンクされておりますので、各チームの成果、ぜひご覧いただいて、ご意見等ございましたら、メール等でお寄せいただければと思います。それでは私から、汎用グループの成果の説明を終わりにいたします。
続いて、ここからはパネルディスカッションの方に移らせていただきたいと思います。それでは、汎用基盤技術研究グループのパネルディスカッション。テーマは、Challenges in Mathematical Machine Learning です。それでは、登壇者をご紹介いたします。杉山正史グループディレクターです。それから、チビン・チャオチームリーダーです。それから、今泉正明チームリーダーです。それから、伊藤真二チームリーダーです。それではどうもよろしくお願いいたします。
Okay, thank you very much. So we need to start speaking in English from this session. So my name is Masashi Sugiyama. I'm chairing the session. So it's my great pleasure to invite three PIs, team leaders in the fundamental groups. So they are really doing excellent research. So first of all, so I will ask each of them to briefly introduce their research. So maybe in 1 or 2 minutes. Then, so Chibin, would you please start?
My team's research mainly focuses on tensor methods for machine learning. So tensor decomposition and tensor networks are fundamental mathematical tools for efficiently representing high-order structured data. And our goal is to develop advanced tensor decomposition methods to handle with various complex situations, and then we leverage them to address key issues in machine learning. So in this fiscal year, we have developed a very flexible tensor decomposition method, which can capture nonlinear tensor structure and also can learn the unknown distribution of the data. For tensor networks, we have developed a very fast algorithm which can find the best optimal tensor network structure for the given data set. So next slide, please. And on the other hand, so we also address adversarial robustness of deep learning models. So our study found that if model parameters is of low rank structure, the robustness can be enhanced. And we also propose a new learning criteria, which allow us to use any generative model to be adaptive to a purified model, which can effectively remove the malicious perturbation from the input data. So in the future, we will further develop more advanced tensor network algorithm and try to make the future AI more reliable and efficient. That's all.
Okay, thank you very much. So tensors are basically an extension of matrices, right? Matrices are two-dimensional and tensors are three or more dimensions. I think the basics of this tensor methods are basically matrix factorization. You have users and items. If we wanted to approximate a matrix only from a limited amount of observations or something like that.
Yeah.
So, but now the situation is more complex and we have like a three-dimensional or more dimensional object. And also you even consider nonlinear structure. So can you briefly mention a bit about nonlinear structure here?
Yes, basically the tensor decomposition, as Professor Sugiyama mentioned, is based on matrix decomposition, which is linear algebra or linear case. In tensor case, it's multilinear case. But now, due to the very real applications, our data is more complex, and some structure are not satisfy the strict linear structure. So we need to consider nonlinear case, which can capture more flexible data structure, which can find more useful features.
And classically, I think tensor decomposition, metric decomposition was used for like kind of data side. But nowadays, this is also applied to parameters of a big model, like compressing neural networks. So you are also working on that topic.
Yeah, you are right. I think now we also use tensor not only model the real data, but we can also model the deep neural network parameters. If the parameters satisfy some kind of structures which can affect the machine learning model performance, like robustness and other issues.
Not only compression, but robustness is also improved. So that's quite impressive.
Yeah.
Okay, great. Thank you very much.
Thank you.
So then next is Masaki Maizumi-san. So he's a new team leader.
Yes. Yeah. Thank you very much for introduction. So I'm Masaki, organizing the high-dimensional causal analysis team, like a complicated team name. But anyway, so our team has basically two research aspects. First one is the fundamental one, and second one is the application side. And in the fundamental side, we are mainly working on the high-dimensional statistics and the deep learning theory, like analyzing the statistical models which have the huge number of parameters. In the application side, we try to apply the result of the fundamental side to the more practical and more interesting machine learning data science topics, including the code analysis and statistical inference also. Yeah, next slide, please. Basically, so our interest is about our interest is to understand the unsolved issue or unclear problems of the large-scale data science, including the deep learning and artificial intelligence. So this figure shows that what is unclear and what is clear. So, and in my view, my personal view. So, and what I think this does the dynamic. There's two kinds of the models, like deep models and shallow models, and also two kinds of properties, like static properties and dynamic properties. Dynamic means that how models changes when in the learning phase, training phase, and also prediction phase. And in my view, the dynamic properties of the deep models are totally unclear in my understanding. So, of course, in contrast, like a static property or shallow models are somewhat clear, the well studied. So this is kind of frontier, like a boundary between the clear side and unclear side. And our try to extend the clear region by developing a new theoretical result. Yeah. Next slide, please. And also, so the recent is that we are focused on two types of the theories. So to understand the large-scale data science models, so we focus on the theory for fitting, which try to develop a mathematical model which is consistently behaves to the practical phenomenon of the large-scale models by using kind of the physics-based approach. And the second interest is to develop the theory for semantics, to develop the theory which is understandable or interpretable to describe the artificial intelligence and deep learning, including the for example, in context learning theory. Yeah, that's for our recent interest. Thank you.
Okay, thank you very much. So first of all, so welcome to Weekend AIP.
Yes.
So I knew him for many years and I really wanted to work with him. So I'm quite happy that he joined Weekend. So I have actually a question on the second slide already. So before starting the panel discussion, I asked some quick questions.
Yes.
But this static view and dynamic view. So this is, I think, quite interesting. And so, but in the middle, what exists? So I'm sure. So what do you mean by static and what do you mean by dynamic?
Okay.
But what there are in between these two?
Oh, okay. Yeah, thank you for that nice question. So my idea is that there's some research topics which simultaneously considers simultaneous analysis on the static side and the dynamic side. So for example, the neural tangent kernel theory is kind of typical. Typical example of the intermediate point, which can approximate the neural networks by using the kernel function, and also study the dynamic transition of the neural networks by using the kernel functions. That's kind of a combination of the six dynamics, and this kind of ability can provide a very more intuitive analysis result for the understand the deep learning.
I see. So this dynamic part is quite interesting. And suppose you understand something, you clarify something. Okay. What you can really obtain? What we can learn from that?
Okay. So I think that there's two types of benefit. The first one is we can feel happy because we understand the inside of the deep learning. That's kind of a more rough pleasure. And the second one is that we can develop the more efficient tuning method for the hyperparameters.
Efficient in terms of samples or
computation. Yes.
I see. Great, thank you very much.
Yeah.
So then the last is Ito-san. He's also a new team leader. So welcome.
Thanks for the introduction. I'm Shinji-to, and I'm happy to join the Weekend AIP as the leader of new team of sequential decision making. And the goal of this team is to develop theories and algorithms for prediction learning, decision making, and the repeated interaction with external environments. An example of specific areas addressed by this team includes online learning, bandit algorithm, and reinforcement learning. And an example of the recent progress is about environment adaptive algorithm that works well for several different types of environment without parameter tuning by the user. And we also have progress in algorithm for structured sequential decision-making problems and computationally efficient algorithms. Please, next slide. And there are several challenges in my mind that interest me as the next topics that could become increasingly important in the future. One is about online learning and reinforcement learning in changing environment. As Professor Sugiyama mentioned, this would become more important in the context of training of LLM. But I think that one challenge in this field comes from the situation that there are various different types of researches. There are various approaches have been proposed in different research areas, including reinforcement learning, continual learning, and online learning theory. So it seems difficult to compare them, benchmarking these properly. Another challenge in my mind is about multi-agent online reinforcement learning, because I believe that recent advances such as LLM play roles of the interface between different types of applications or AI agents. So there must be more and more interaction between different types of AI systems that learn, update, and change states. So I think this will become more increasingly important. So if time allows, I'm happy to hear. I'd be happy to hear the views of other professors on this topic.
Yeah.
Thanks for the time, taking the time for my introduction.
Okay, thank you very much. So we should definitely discuss that. So, but before that, so let me briefly talk about your research. So I think Ito-san is one of the most successful theoretical researcher in this community. He published, I think, an enormous number of papers in top conferences. I'm really happy to have him here in our center at Weekend AIP. So I'm also interested in reinforcement learning very much. But on the other hand, okay, a lot of research on bandit algorithms were done so far.
Yeah.
But so maybe, so to be precise, I think the communities are a bit separated. So in bandit community, so people are more focusing on like clarifying theoretical properties, showing the like minimal regret or something. But on the other hand, in the community of reinforcement learning, they care more like practical aspect. They try to solve a problem and scalability and things like that. So in the next page, you said, so online learning, reinforcement learning. So these are, of course, in a high level sense, so they are in the same framework. But from your viewpoint, so how can you combine like these two different communities?
It's a very difficult question. One way is to
mathematically, the biggest difference is whether there's a state change between the time steps, right?
Yeah.
So without having state transition, so maybe precise theoretical analysis is possible. But once you have a state transition, then things are extremely complex. Right? Can you somehow find a kind of intermediate point between these two? The reinforcement learning itself is maybe too complex to analyze.
Yeah.
But can you somehow consider a very simplified version of reinforcement learning that still has some essence of state transition?
That's almost the same. In your point is almost same as the opinion in my mind.
Yeah. But my problem is I don't have any mathematical background, so I'm just saying some ideas. But I think this is quite important because now reinforcement learning is really becoming an important tool, even in large language model communities. But still, theories are still behind, I think, compared with like other sequential learning techniques.
As you mentioned,
including online learning and bandit theories. So having some elementary theory for reinforcement learning must have a big impact to the community. It should be really explored. Okay, thank you very much. So already the topics are quite deep and it's not that easy to follow. And also I didn't really prepare any questions in advance. So we really want to have like random discussion based on some slides before. So then I skipped basically this slide from Imaizumi-san. And like, you have nice theory for like in-context learning. So this is quite kind of fancy topic.
Yes.
Can you elaborate this one a bit more?
Yes. Yeah, it's a very ongoing topic, but I'm actually, interested in like in-context learning, which is kind of the theoretical framework which you to analyze like fundamental models, such as the ChatGPT also. And first, maybe understand that the ChatGPT is kind of a black box, so you want to, understand the inside of the ChatGPT. And so, the recent progress says that what occurs in the transformers ChatGPT for in-context learning, and what kind of the data is very beneficial for the like transformer ChatGPT. So that kind of ideas are not so beneficial for so that transform. That's kind of so we try to develop the new theory to describe like the advanced.
Yeah, so that sounds really new to me.
Yeah,
And to be honest, I can't really understand how you approach this problem. So can someone briefly describe the framework for that?
Yeah, basically, so my research tool is like a statistical analysis. That's kind of my one of my backgrounds. And the typical case is kind of the sample complexity, like how many samples and pre-trainings are necessary to make a very clever AI, and also the lengths of the prompts. How length the prompt should be to understand achieve the, like a nice GPT. So that's kind of
So sample complexity of the prompt.
Yes. Yeah. That's kind of as the first step. That's our
So nowadays, I think designing prompts is really important.
Yes.
Initially, it was more like engineering, but now it's like an AI topic. Right? We want to automatically generate efficient prompts. Planning.
Yes. So I mean, basically, in our analysis, as the first step, so our design of the prompts are very simple. Like every prompts are vectors, elements of the Euclidean space, and like a very nice linear space. But that's the first step. And after we complete the step, we can go to the more like a complicated mathematical setup. Like prompts are more like a manifolds or like a non-Euclidean space or so. And we can like I hope that we can suggest a more like a efficient design of the prompts in the mathematical sense by using our theory. Yeah.
So once we construct prompt engineering, then the adversarial attack is also possible in the layer of prompts. So I think Chibin is an expert on adversarial issues. Have you thought about any like issues on prompt engineering in the context of adversarial training?
Yeah, for me, currently we haven't worked on this, but we understand that large language model also has such problem if prompt attack. And this is a generative model, so it's slightly different with supervised model attack. So I think they are more challenging than the supervised model.
And already the system is deployed and running, right?
Yeah.
So in that case, how do we approach the problem? This is really challenging.
Yeah, we should be fast.
But so is it again kind of repeating game? If you propose a new method, then somebody can easily break it and just repeating the same thing forever.
Yeah, and so far I think there is no solution to totally solve this problem. It's like a safety problem, reliability. So people can always find a good way to attack or to find the prompt attack to make your model give the wrong answers. But I think this problem is still very important. It's worth to study. Maybe we
need to anyway first understand what is really happening and going on in the system.
Yeah, maybe theory is more important to understand why such problem happens.
So I mean, you mean adversarial?
Yeah, robustness and vulnerability.
Oh well, it's a very difficult question. So and even for the very simple models, there are several like discussion about the effective or the kind of the inside of the adversarial point. And in the supervised model, like every input's a vector, so easy to analyze. So it's kind of the understandable and controllable. And I don't know much about like the recent advance, but I think I can image that how to analyze like a supervised model. But in large language models, so everything are not vectors, not mathematical. So I mean, for me, it's not very easy to understand the inside. What's the road of the adversarial attacks? Yeah.
So I want to stick to generative AI for the moment because this is a really hot topic and important even for generic technology research group. So now, okay, large language model is there already and it is deployed and running. So but every day new things are happening. Then we need to update the model. But clearly retraining the system from scratch maybe takes a few weeks or a few months. So it's not really possible to do that every day. Then basically online learning is the only way to go. And some people may call it fine tuning, but I don't want to call it fine tuning. It's online learning, so it should be a more serious learning. Then so it goes on topic. So your work so far was not really focusing on generative AI, but can you somehow naturally extend the current or existing or previous theories in the context of large language models or generative AI?
Yeah, I believe so. But there are many hurdles, there are many difficulties to apply the theoretically guaranteed techniques because there is a as you mentioned, there are a large gap between theory and practice in terms of the complexity of models. As far as in my understanding, the scope of the current bandit theory or online learning theory is basically focusing on linear models. So, but LLMs or neural networks are clearly non-linear. So,
but can you just chop the big model in the last layer and fix the first part, feature extraction part? Then the last layer is basically a linear classifier. Then can you somehow approximately apply a linear theory to?
Yeah, I believe so. And such types of approximation speed, research area of it.
I partially more
sense of approximation.
yes, of course, the recent approximation theory for neural networks goes beyond the linear phase. So in the classical theory, classical function analysis, the functions kind of have a linear sum of the basis functions, but the recent neural networks has go beyond the linear sum of the basis functions. It can application more complicated function. That's kind of the great recent progress. But in contrast, in the study, the dynamics of the neural network, so everything's much more difficult. So because it has the stochastic, the randomness, and the randomness is really kind of the source of the difficulty, and in the randomness of the field, non-linear analysis is totally impossible, almost impossible, I think. So, and we have to, we cannot go beyond the linear regime. So, in a sense, in the non-random case, the goes to non-linear is okay, but the random field, linearities are very, necessary. So, it's a very source of the difficulty.
But maybe previously you talked a bit about neural tangent kernels.
Yes.
So it's basically local linear approximation.
Yes. That's a source of reason why it succeeds.
But some people may criticize that's quite different from the practical deep learning.
I totally agree. Yes.
So do you agree on that?
Yeah, I totally agree that. Yeah, it's kind of basically it's a linear model, but a very useful linear model. It is practical in some cases, but in many other cases it's not so very practical. It's not fit to the practical model. So of course there's a clear limitation of the NTK theory, but it's still an interesting theory.
So personally, I have worked on distribution shift, so changing distribution for many years.
Okay.
So then in the context of large language model or huge foundation model, so I think overcoming changing environment is really a key issue. So do you have any ideas or theoretical aspect that need to be studied in this context? So Ito-san's topic is already quite directly related, but can you try to explore that topic? So from the bandit theory in the beginning, or what's your plan?
Yeah, so plan is beginning, but yes, first, what we should do in the first step it would be to align the types of non-stationarity. There are various types of non-stationarity. One is about, for example, the environment is non-stational, but one type in easier setting, the environment can be non-stationary, but the optimal action does not change. In the further situation, the optimal action can be changed. So, and there are more other different settings of non-stationary environments. So
I see.
First thing we should do is to align or to say to model the different types of non-stationarity and consider the method that matches each of them.
In the case of standard prediction problem, so we have only input and output. Then basically the distributions are a joint distribution of input and output. But in the case of sequential decision making, so we have transition probability, reward function, and many other things behind. So we need to have a kind of unified framework to formalize the changing distribution first. That's, I think, completely missing important step. So I expected to have more time, but already, so we only have 5 minutes. So then I wanted to ask like a more serious question. Then, so like we are theoretical researchers. Then often our research is quite bottom up because we are just curious on like, tackling this problem and that problem. But of course, in the reality, so life is not that easy. So there are a lot of demands in the world. And so our important job is to match the bottom up curiosity and real world demand. So then, so I want to ask each of you. So what's your personal curiosity, behind? So you don't really need justification, but what do you think it's fun to do research? Then also try to think of like connection of your interest to some real world requirement, real world challenge. So let's start from personal interest. So what kind of topic are you interested in? Don't think about applications at this moment.
Yeah. So for me, because our research is a little bit more fundamental, my personal interest is we would like to develop some technique or technology which may change the future AI dramatically, like transformer or like a generative model. So of course, this goal is too big, but this is my interest and my vision. So some basic technique which may change the future AI whole structure.
Okay, yeah. Thank you for the question. So yeah, for curiosity, I have 2 types of curiosity. The first one is within the fundamental research. So I really enjoy the study that like a complicated, knowledge or theory, new theory in the fundamental side. So it's very fun for me. So that's one curiosity, and I want to understand more like a complicated, useful theories. And the second curiosity is to apply the nice question from the application side, which can deliver to the like a fundamental side. So like not the knowledge, but a question. The new application give us a new, very nice question or motivation to develop the new theory. So it's really fun for me. So I want to understand like recent technologies and the extract a nice question or motivation and deliver it to the like fundamental like a new theory. That's my second.
I see. So in a sense, you need to simplify the real challenge and formalize it in a mathematical way, in the simplest way.
Yes. Yeah. I think that's one of the most interesting points in this field.
Yeah, great. So then, Ito-san, how about you?
Yeah, my curiosity comes from my trouble in decision making in personal in daily life.
You want to optimize your life, right?
Yeah. I feel it's very difficult to make decisions under uncertainty in the future and changing environment. So I want to make a methodology to make a good decision or justify what types of decision is rational. So that's a source of my.
So rational does not necessarily mean optimal.
Yeah.
So do you also want to like mathematically formulate that kind of issue?
Yeah.
But this is actually quite important.
Yes.
So like in the field of maybe economics, econometrics, maybe that kind of human factors are also modeled and taken into account. Maybe that's still missing in the machine learning community. Because we only hear prediction accuracy and things like that.
I agree that rationality and optimality are totally different. And there are many ways to define them, and it's big.
Yeah. So then, Chibin, you have 3-4 minutes to think about this, the connection. So based on your personal curiosity, so what kind of real world challenge could be connected? You don't have to say like this problem can be solved, but what do you think of the possibility?
Yeah, I think reliability is one issue. I think it's possible to be solved in the future, and it's necessary to be solved. So now we try to focus on these issues and to at least make AI more reliable and robust.
So in particular, so all the real large language models are deployed, and So improving the reliability is guaranteeing the reliability is really a key issue nowadays.
I think so.
So you believe that tensor kind of research can contribute to that field?
Yeah, I believe tensor, if we use tensor well, we can find a good way to solve this problem. Of course, we also need other technique, not only tensor, but maybe some generative model, like a diffusion or some other.
Oh, great. So then Imaizumi-san already talked about both directions, but then so it's nice to have one or two nice examples.
Examples? Well, yeah. Now we are now going to statistically formalize the LLM, large language models, and what it solves and what optimally means. We try to clarify that point. Yeah, that's kind of my ongoing work, and it's very interesting.
So then, Ito-san, how about you? So already you try to connect your rational decision to mathematical theory. So do you also have some specific target in your mind?
Yeah, but it's too technical ones.
Yeah, go ahead.
So one is to adapt to the, sorry, it's hard to explain in English. So
Can you speak in Japanese in that part? So this is also fun.
the way of connecting the curiosity and
But then, all right, so fine. So think about it carefully. So, like generic technology research group is mostly consisting of theoretical researchers, but this does not necessarily mean we are simply free to do, basic research. Of course, we should always care the real world challenges, but so at least our research should be somewhat motivated from the real world challenges. So this is, I think, important message to the society that so we are theoretical researchers, but we are working on theories, not only theory for theories, but theory for practical problems. So this is something we should always bear in our mind and hope that our theoretical achievement can really contribute to drastically improving the reliability, safety of AI systems in the future. So that's a kind of common challenge for Weekend AIP. So then it's almost time and we need to conclude the session. Thank you very much.